Welcome to a lesson with Dr. Powell. Let's take a look at nested fiber boxes. Let's let G be a function whose fiber box diagram is given by the smaller fiber boxes. So the codomain of G is 1, 2, 3, 4, 5, 6, 7. And then the fibers of G are just what you fill in right here. So what maps to 1, what maps to 2, what maps to 3, and so forth. These things must not overlap in order for this function to be well defined. So no two things are trying to be sent to the the same thing isn't being tried to send to different places. Just each thing is sent to exactly one place, so the function is well defined. Okay, so that's G. Now F, let's let that be the larger fiber boxes, the larger ones. So the codomain would be 1, 2, 3 according to this diagram. We're going to label that as C. The codomain of G is B. And notice also we're going to require that. So what is in the what are in the fibers of F? Because you see these boxes here, we're going to assume that both G and F have the exact same domain, so that actually the fibers of F are just going to be the innermost numbers. And so we can draw a little diagram over here just to kind of emphasize this fact. A fiber box diagram would be 1. We could think 1, 2, 7. So these are the numbers that map to 1 via the function F. So notice we're ignoring these extra things in here. We're just going to take 1, 2, 7, the innermost, and putting those together. Then the fiber over 2 would just be 3, 4, 9, and 8. And the fiber over 3 would just simply be 6. So we're just kind of looking at the different fibers, and we notice that the fibers of G fit nicely inside of the fibers of F, except for an empty one, but that's okay. An empty one can sit off to the side and it won't count in this particular situation. Okay, so with that in mind, we actually get, because we have this nesting, aside for an empty, we naturally can say that we have a function, a well-defined function, or we can define a well-defined function from B to C. Let's just call it H, such that when I first do G and then do H, like I first put something through G, then put it through H, I compose it, it'll have the same effect as if I just went through F. We call that a commutative diagram. So let's think about that. For instance, how would the function H work? Well, the function H is going to go from B and it's going to land in C. In fact, you should be able to see exactly what this function is just about already. Okay, in fact, we already kind of see it. So, I mean, it almost works. What if we were just to go through and erase this 1, 2, and the 7 right here? And we won't exactly do that right now, but just imagine that those aren't there. And so we have 1, 2 is being sent to 1. 3, 4, 5 is being sent to 2. So 3, 4, 5 is in B, and 6 is in B. So 6 is being sent to 3. So you know exactly where 6 is sent, 3, 4, 5 is sent, and 1, 2 is sent. We actually have a well-defined function, except we don't know one thing. We don't know where 7 is sent. And really, we can send it to anything and have this diagram still commute, because all that was important was that when we first, well, let's just try something. What if we start with like 1? What is G to it? G sends 1 to 1. And what does H do it? So you can even see this. So it sends, we take 1 in the domain, we send it to 1 in B, and then what do we do with that 1? We send it to 1. Well, that's exactly what F would do. F would take this 1 and send it to 1. And we just had an intermediate step right here, this one. So we just went here to here to here, or we could just go from here to here. That's really all we're doing the whole time. For instance, if we start at 7, G will take it to 2, but then we'll go to 1. Well, that's the same thing as just bouncing down to 1. So really we can see the commutative diagram right here in these arrows. Or here, first take 9, you can send it to 5 and then to 2, or you can just send straight to 2, but it will work. So we have this commutative diagram. A commutative diagram can be seen by nested fiber boxes, or it can be, or just as a picture right here, where we're thinking of compositions, where we have first do G, then do H, is the same thing as just doing F. And we put this little arrow here sometimes to mean that the diagram is commutative. Now, this lonely 7 doesn't really mean anything because really there's nothing in A that corresponds to this point, so we're good. It's out of the picture for commutativity, because really commutativity only worries about things that start at A. So whatever starts at A needs to be nested, have this nesting from the fibers of G and the fibers of F. And if fibers of G sit inside the fibers of F, then we have a natural map or function that goes from the codomain of G to the codomain of C, just like that. As long as we maybe modify the function slightly to account for anything that's outside. So let's suppose if we just kind of threw this into this fiber, just made it a little bit larger right here for 3, then at least for the function H. So these guys really are in the domain of H. So that's where they come in. 1, 2, 3, 4, 5, 6, 7 are in the domain of H. And we can really just extend any one of these fiber boxes to include empty fiber boxes that were there from G, and we have a well-defined function. And I guess in this particular case, I was just using that to show existence. There exists such an H. This H is not unique because of where we could throw the 7 into these different fiber boxes. Thanks for watching.